Great analytics detectives solve analytics-related mysteries using the power of Microsoft Fabric and Apache Spark because you have a secret weapon, your trusty notebook. No, not the one with paper pages, but the one where you can write and run code in multiple languages, combine text, images, and charts, and collaborate with other detectives. With this notebook, you can harness the distributed processing capabilities of Spark and the rich set of libraries available for data engineering and analytics. Welcome, detectives. My name is Jason Richards, Microsoft Technical Trainer and Data Detective. Let's uncover the clues on how to use Spark and Fabric to load, transform, and query data using dataframes and SQL, as well as how to create stunning visuals to reveal insights from your data. Ready? Let's begin. Before you can start your investigation, you need to set up your Spark cluster in Microsoft Fabric, where you can manage the configuration and environment of your cluster. This is the mystery of the cold case cluster. Apache Spark is a distributed processing framework that enables large-scale data analytics by coordinating across multiple processing nodes in a cluster. Put more simply, Spark uses a divide-and-conquer approach to processing large volumes of data quickly by distributing the work across multiple computers. The process of distributing tasks and collating results is handled for you by Spark. You submit a data processing job in the form of some code that initiates a driver program, which uses a cluster management object called the Spark context to manage the distribution of processing in the cluster. In most cases, these details are abstracted. You just need to write the code required to perform the data operations you need. Spark can run code written in a wide range of languages, including Java, Scala, a Java-based scripting language, Spark R, Spark SQL, and PySpark, a Spark-specific variant of Python. Most data engineering and analytics workloads are accomplished using a combination of PySpark and Spark SQL. In Microsoft Fabric, each workspace is assigned a Spark cluster. An administrator can manage settings for the Spark cluster in the Data Engineering Science section of the Workspace Settings. Specific configuration settings include the node family, which are the type of virtual machines used for the Spark cluster nodes. Currently, memory-optimized nodes are the only option. The runtime version of Spark and dependent subcomponents to be run on the cluster. Spark properties are specific settings that you want to enable or override in your cluster. The Spark open source ecosystem includes a wide selection of code libraries for common and sometimes very specialized tasks. Since a great deal of Spark processing is performed using PySpark, the huge range of Python libraries ensures that whatever the task you need to perform, there's probably a library to help. By default, Spark clusters in Microsoft Fabric include many of the most commonly used libraries. To set additional default libraries or persist library specifications for code items, you need workspace admin permissions to create an environment and set the default environment for the workspace. The environment item in Fabric is currently in preview. There you have it. Having ready-made cluster options at your disposal is essential for solving mysteries that require special clue-cracking settings. Whether you need to crack a case that involves interactive exploration and analysis, or automate a process that ingests and transforms data, Fabric has the tools you need. You can use notebooks or Spark jobs to run your code on Fabric clusters and leverage the power of Spark to handle large-scale data processing. Let's dive into the details of these options and see how they can help you solve the case of what we'll call the enigma of execution. To edit and run Spark code in Microsoft Fabric, you can use notebooks, or you can find a Spark job. When you want to use Spark to explore and analyze data interactively, use a notebook. Notebooks enable you to combine text, images, and code written in multiple languages to create an interactive item that you can share with others and collaborate. Notebooks consist of one or more cells, each of which can contain markdown formatted content or executable code. You can run the code interactively in the notebook and see the results immediately. If you want to use Spark to ingest and transform data as part of an automated process, you can define a Spark job to run a script on demand or based on a schedule. To configure a Spark job, create a Spark job definition in your workspace and specify the script it should run on. You can specify a reference file, for example, a Python code file containing definitions of functions that are used in your script, and a reference to a specific lakehouse containing data that the script processes. All right, so the enigma of execution is a closed case. Flexibility in executing Spark code just adds to our capabilities to solve analytics mysteries. Now let's investigate how to work with data in a Spark data frame, a data structure that enables you to process large volumes of structured or semi-structured data efficiently. This is the case of the distributed data frames, and we're on it. Ready to get cracking? Let's go. Natively, Spark uses a data structure called a Resilient Distributed Dataset, or RDD, but while you can write code that works directly with RDDs, the most used option for working with structured data in Spark is the data frame, which is provided as a part of the Spark SQL library. Data frames in Spark are similar to those in the ubiquitous Pandas Python library, but optimized to work in Spark's distributed processing environment. In a Spark notebook, you could use the following PySpark code to load the file data into a data frame and display the first 3 rows. The first row of the CSV file contained the column names, and Spark was able to infer the data type from each column from the data it contains. You can also specify an explicit schema for the data, which is useful when the column names aren't included in the data file, like this CSV example. Specifying an explicit schema also improves performance. Now, the examples we show here are for CSV, but the Spark engine can natively load in several file formats, including JSON and Parquet. Now that we have our data on our notebook, time to use our deductive capabilities to interrogate, manipulate our data to reveal their secrets. For example, the following code example uses the select method to retrieve the product ID and line item total columns from the data frame named DF containing product data. In common with most data manipulation methods, we want to make sure that when changing a data frame, we want to apply a new variable name so as not to overwrite the existing data frame. Here, we set a name of pricelist_DF on the left side of the equal sign to make that happen. You can also chain methods together to perform a series of manipulations. For example, this code chains the select and where methods to create a new data frame containing the product ID and line item total columns for products that had an order quantity of 1 and 2. To group and aggregate data, you can use the group-by method together with aggregate functions. For example, the following PySpark code counts the number of products for each order quantity. Any changes made to the data frame are saved in memory, so it's always a good idea to occasionally externally save your transformed data to ensure if something should happen, and everything fails at some point, then you have the peace of mind knowing it's externally saved. The following code example saves the data frame into a Parquet file in the data lake, replacing any existing file of the same name. The Parquet format is typically the preferred file format that you'll use for further analysis or ingestion into an analytical store. Parquet is a very efficient format that's supported by most large-scale data analytics systems. In fact, sometimes your data transformations requirement may simply be to convert data from another format, like a CSV file, to Parquet. Partitioning is an optimization technique that enables Spark to maximize performance across the worker nodes. More performance gains can be achieved when filtering data and queries by eliminating unnecessary disk input-output. To save a data frame as a partitioned set of files, use the partition by method when writing the data. The following example saves the data frame DF and partitions the data by year. The folder names generated when partitioning a data frame include the partitioning column name and a value in a column equals value format. So the code example creates a folder named data that contains the following subfolders: year of 2020 and a year of 2021. Each subfolder contains one or more files with the product data for the appropriate year. Here, our data frame only contained 2 years of data for 2020 and 2021. If there were more years of data represented in the data frame, then the partition by function would create additional folders for those years. Now here's where this gets exciting. When reading partition data into a data frame, you can load data from any folder within the hierarchy by specifying explicit values or wildcards for the partition fields, saving computational time and costs. Way to go, detectives. We cracked the case of the distributed data frames. Spark is a very flexible programming language, but what about our fellow detectives that only work with SQL? Never fear, Spark SQL to the rescue. Spark SQL is a powerful library that lets you work with data using SQL expressions. Spark SQL enables you to create and query relational data objects in the Spark catalog, such as views and tables, and Spark SQL gives you the flexibility and performance you need to crack any case. Let's dive in. The data frame API we worked with earlier is part of a Spark library named Spark SQL, which enables data analysts to use SQL expressions to query and manipulate data. The Spark catalog is a metastore for relational data objects like views and tables. The Spark runtime can use the catalog to seamlessly integrate code written in any Spark-supported language with SQL expressions that may be more natural to some data analysts or developers. It's important to note that Spark SQL can only be used when the data is in a format that allows for SQL querying, meaning tables and views. One of the simplest ways to make data in a data frame available for querying in the Spark catalog is to create a temporary view as shown in the first code cell here. This view is temporary, meaning that it's automatically deleted at the end of the current session. You can also create tables that are persisted in the catalog to define a database that can be queried using Spark SQL. Tables are metadata structures that store their underlying data in the storage location associated with the catalog. In Microsoft Fabric, data for managed tables is stored in the table storage location shown in your data lake, and any tables created using Spark are listed there. You can create an empty table, or you can save a data frame as a table by using its save as table method like shown in the first code snippet. Deleting a managed table also deletes its underlying data. Additionally, you can create external tables. External tables define metadata in the catalog, but get their underlying data from an external storage location, typically a folder in the file storage area of the lakehouse. Deleting an external table doesn't delete the underlying data. As a note, you can apply the same partitioning technique to Delta Lake tables like we did with the Parquet files earlier. Partitioning tables can result in better performance when you're querying them. There are different ways we can use Spark SQL to query data once in the proper format. In this first code block, we see that we're using PySpark and its SQL function to include a SQL string value in the argument that contains the query we want to run. This requires us to display the results, so if our detectives are more familiar with Pythonic language, this is just right. For detectives who prefer to use native SQL to query data, there's another option. The percentage SQL line at the beginning is called a magic operator and tells Spark that the language used in this cell is going to be SQL. You can select the language you want to use as a default in the toolbar of the notebook interface, and then use a code magic operator to override that choice for a specific cell. Pretty nifty, huh? Rest assured, SQL sleuths, that Fabric isn't leaving you out of the fun when it comes to analytics detecting. Sometimes the best way to solve a mystery is to look at the clues in a different way. That's where data visualization comes in handy. Data visualization is the art and science of presenting data in a graphical form that reveals patterns, trends, and insights that might be hidden in plain text or numbers. This is the case of the vexing visualizations. Are you ready? Let's go. One of the most intuitive ways to analyze the results of data queries is to visualize them as charts. Notebooks in Microsoft Fabric provide some basic charting capabilities in the user interface. When you use a display method on a data frame or run a Spark SQL query in a notebook, the results are displayed under the code cell. By default, results are rendered as a table, but you can also change the results to view a chart and use the chart properties to customize how the chart visualizes the data. The built-in charting functionality in notebooks is useful when you want to quickly summarize the data visually. When you want to have more control over how the data is formatted, you should consider using a graphics package to create your own visualizations. There are many graphics packages that you can use to create data visualizations in code. Python supports a large selection of packages, most of them built on the base matplotlib library. The output from a graphics library can be rendered in a notebook, making it easy to combine code and visuals in the same place. The matplotlib library requires data to be in a pandas data frame rather than a Spark data frame, so the toPandas method is used to convert it. The code then creates a figure with a specified size and plots a bar chart with some custom property configuration before showing the resulting plot. You can use the matplotlib library to create many kinds of charts, or if preferred, you can use other libraries like Seaborn to create highly customized charts. All right, we're visualizing the finish line, detectives. Spark is just one way of working with data in Fabric, and we'll cover other methods as well. Now that we've collected all our clues in solving Spark-related mysteries, we can hop right back into the Detectolab 5000, aka my Surface laptop, and put knowledge to practice. The game is afoot.
All right, everybody, welcome back to the environment. We're working with Spark here, so a lot of concepts to cover. Let's cover it real quickly. So I'm in my workspace, and when we work with our Spark pools are assigned by workspace. So when I go into workspace settings, this under the data science and engineering is where I can manipulate these. Now keep in mind that at the time of this recording, this is how the user interface is set up. Just know that sometimes these options get moved around and things like that based on feedback and other items. So don't think that just because it's here doesn't mean necessarily it's going to be there if you're working on it later on down the road. Just pointing that out. All right, so what are we working with when we're working with Spark? We're working with pools of virtual machines, essentially. So several virtual machines that are executing the work on our behalf. So we always get a starter pool or a default pool for everybody, and they name it starter pool. I can create workspace pools if I wanted to. So I can go in here, I can give it a name. I can memory optimize means that it's CPU enabled, and then I can vertically select the size for each of the virtual machines for each node. Now, small, as you get larger, there's more RAM and memory included in these. And for, larger data workflows or more complex data operations like experimentation and model building, we may want to use larger sized nodes for that. That's the vertical way we can scale up or down these, by the way. After we create one, we can go in, management, drop it, scale these on demand. Horizontal scaling is another way we scale, and that's adding another virtual machine essentially to perform the work. So we're doubling the work. So each one of these nodes represents its own virtual machine. Here we're telling it to auto scale. So when the job is submitted to the Spark engine says, well, I probably need this many nodes in order to perform this work the most efficiently. It's got an optimizer in that. So it may deploy only 2 nodes. If I have auto scale, it may deploy up to 10, depending on that. So this is another way that we're kind of releasing some control in order for Spark to self-optimize that. Once I have a pool created, then I can do things like add an environment. It comes with a default environment. I can set libraries in that environment if I need to. And there's some other settings, like if several users or services are going to be utilizing this compute option or this pool, I can enable high concurrency, just meaning more users can use it at the same time. And then automatic logging, which is ML flow enabled logging for machine learning experiments and models. All right, good stuff. Now, in order to open up a notebook, well, you can either go into the data science or the data engineering experience. I'll just go into data engineering since that's kind of the focus of this course anyway. And I can import notebooks or load existing notebooks in here. Now that I've already imported one, but you can get it from your local system once you have it in there. So when I go back into the workspace, you can see that I can open up the notebook from here. Now I won't get into notebooks necessarily in this particular demo because we're going to cover notebooks in another one. But I will kind of say that, you know, the Spark engine or the different languages that we can use, so Python, Scala, SQL, and R in here, you can see that the default for this one is set to Python. That's the code that's being used in here. And you can see some of the other options that we have set in here. So we'll go ahead and stop this session just because I want to show you what happens when we execute a cell. So I have canceled this session on here. Obviously I come in here and practice this and see what errors might happen when these get executed. But when I execute my first cell, it'll attach to a session. How long would this take in another type of platform service? It could take 3 or 4 minutes, but you can see here that my session started in about 3 to 5 seconds. This is the benefit of having that one node on all the time. So what I'm doing here, and I'll kind of go through what the Python is telling, or I'll tell the story of the Python as we're doing this if you're not a Python expert. Totally understandable. This isn't the only way to have to work with data in here. There's several other ways. So if you're more of a SQL person or just understand logic, we got solutions for you. This is just one way of doing things. But what we are doing is importing libraries. So just because we have them installed on the runtime doesn't mean that it's attached to the session yet. So we need to make sure that we install these. So matplotlib is a visualization library, so a Seaborn. And then we're also importing pandas, which is a Pythonic data frame manipulation. So it creates data frames. They're just pandas data frames. Good to point out that pandas data frames do not equal Spark data frames. This is a Spark engine. If we created a Spark data frame, some tools like matplotlib can't work with Spark data frames natively. So we'll have to convert those into a pandas one. And if there's other Python libraries that are dependent on pandas data frames, they won't work with Spark data frames and vice versa. So you got to keep that in mind when we're working with this kind of information. So I've imported these libraries. Now what I'm going to do is I'm going to get this data set, right? Oh my goodness, I found an error. I thought I handled all these. Well, errors happen. And this is fine. All that happened here is that it can't find this module. And I can do a quick fix on this, right? So I'm going to add a code cell above here. And I'm going to do a pip install real quick of that. So a pip install Azure ML open data sets. So this is a quick fix. Oops. Pip install Azure ML dot. Oh, probably because I didn't spell data sets right. See how syntax matters? But hey, you know what? This is what happens when we run live demos too. Live recorded demos, whatever. Anyway, so what this is doing now is it's installing this Azure ML.open datasets package onto the runtime so that I can execute it later. Now this is happening in the session. So it's attaching it to the in-memory session. The library isn't necessarily installed on the runtime itself all the time. So I would have to literally run this, execute this every time I wanted to do this. So this would be one of those things that I would maybe want to go ahead and add that library into my environment later on. I hope that installed it. Yep. So now what's happening? Now I'm not getting the error. So obviously it did install. And you can see that what we're doing here is from that library I just imported. Azure offers a bunch of publicly available libraries. You can see this is the New York City yellow cab data set. And then I'm importing some datetime parsers or ways to, this declares datetime objects, and this allows me to create arguments from those types of, a datetime object, right? So what I'm doing is I'm setting this parser, and what I'm doing is I'm setting an end date and a start date. So you see I'm using the end date in arguments in the actual New York yellow taxi cab data. When I run this method, you can see that I'm inserting the start date and end dates. These are called variables. When I place something next to an equal sign and run a function on the other side of the equal sign, I'm essentially assigning this to this variable. So that means I just don't have to write this whole thing out when I want to declare something like this. So this saves me coding space, right? So I'm setting two variables here, which is a start date and an end date. And then I'm executing a method called New York City yellow TLC, whatever the TLC is. So when I execute this function, it's going to import this data set for me. But I don't want to import the entire thing. So I'm saying just import where I've defined the start date and the end date. Right, so it's only going to load a month's worth of data, it looks like. Also, I'm converting this to a Spark data frame, right? And then what I'm doing here is I'm using a display method to output this. Now, when I use a display method, it generates a nice rich output for me. And because of that, I can view it as a table, and I could view this as a chart. So this is one of the visualization options we can actually use, right? I can manipulate this. I can create custom charts if I want to, meaning I can change the type of chart that I want to create. So instead of a bar chart, I could say a column chart, and I could switch the keys and values and any aggregations I want to apply to it, as long as it has the data to run that in there. So this is one way that we can create visuals in here, is by displaying this rich HTML output and then convert these. And then I can take these images and download them, export them out, and use them in reports if I wanted to. But I also have a visual in here. This is always good to perform on-the-fly analytics of what visually is happening to the data. Sometimes it helps us understand that a little bit better. All right, so now what am I going to do with this Spark data frame now that I have it? I'm validated, so this is my sanity check. I know that it converted this into a Spark data frame. I'm seeing it. Now what am I going to do with it? What I'm going to do now is I'm going to use SQL context. Now, yes, the Spark engine, essentially way down at the bottom in the foundation of it, in that engine is a SQL engine, right? So it's built a lot of these other data frame packages and everything else are built on top of this. So there is SQL at the base of this. So what we can do is we can use Pythonic code to apply SQL methods. So that's what this SQL functions library allows us to do from PySpark. And then I'm importing everything. And then what I'm doing is just applying methods that are associated with this library, which are very familiar to some SQL statements, right? Select. So select is a SQL statement, and I'm selecting certain columns out of this table or out of this data frame. Sorry, let me correct myself in there. I'm also parsing out information of some columns and then renaming them other names. So that's what alias does. So this would be as, like an as statement in SQL. The filter is like a where clause, right? So dot filter is like a where clause. And what I'm doing is I'm applying several different where clauses to this. So the passenger count has to be greater than 0. The tip amount has to be greater than 0. The fare amount has to be between $1 and $250. And then the trip distance has to be greater than 0 and less than or equal to 200 miles, I'm assuming, because we're in New York City, right? And then what I'm doing here is creating a temporary view. So This right here, since I'm using a filtering clause and I'm applying all these SQL methods to it using Python, I'm saving that as a data frame called filter df. So again, I'm setting this variable, but I don't want to call it df because then I'd be overriding the original data frame, and we don't want to do that. So this is why we rename data frames every time we change it. The other thing I'm doing in here is I'm changing it to a view. Now keep in mind that this isn't a SQL table yet, right? Or something that I can natively query with SQL because it's not in a view or a table format. I can't use native SQL until it's in something like that. So what I'm doing is I'm running this method here called create or replace temp view. This could also be temp table. This could also be table or view. And creating this temporary table called taxi dataset. Now, because I have it in a view format, right? And I didn't set this as a variable. I'm just naming it a table called taxi dataset. Now I can run native SQL statements on here. So I'm going to run this and explain what's going on as I'm doing this. What essentially I'm doing is you see this percent SQL sign. This is called a magic operator. And because there's 2 percentage signs, it applies to the entire cell. What I'm doing with this is I'm essentially overriding the default language of Python and telling it that what I'm going to write in this cell is going to be native SQL. Now, if I hadn't converted this to taxi dataset, which is what I'm referring to here, it wouldn't be able to do this for me. It wouldn't be able to run this query for me. But because I've converted this into a view, now it's going into the cache, looking at the view that I've created called taxi dataset, and now it's running the query on this. Because this is in a SQL, we're calling on native SQL language, it's going to automatically output that rich HTML output. So I can still go change, to chart views or table views and modify how I want to look at the data doing it this way. As long as it's in that view or in a table, I can do this, right? So let's move on and get to going. So what we're doing here is we're going to create another data frame. And what I'm doing is I'm taking a sample of that filtered data frame that we created earlier. Running this takes that data set that we originally had, and I just want to sample a certain percentage of it, right? And randomize it by a seed value. So I'm just essentially taking a sample of the data set that we had filtered earlier, right? And one of the reasons that we're doing is that we're going to convert it into a pandas data frame. Now, converting a Spark data frame to a pandas data frame takes quite a bit, and that's why we're sampling this down. So we're down sampling it in order to convert it to a pandas data frame so we can run these pandas data frame friendly visualization packages on it. Just as a sanity check, I'm running a pandas method called head, which allows me to see the first 5 results of the data frame that was created. So now I know it's in a pandas data frame. Now, because it's in a pandas data frame, I can go through and create visualizations. So right here, what I'm doing is I'm using matplotlib to create a histogram, right? So distribution of tip amount distribution going down. So there's tip amounts. Okay. See a lot of between 0 and 250 happening here. Now what I'm doing here is I'm using Seaborn. So the PLT, since I have matplotlib now I already installed this, but I just wanted to put this here so you could see that the PLT is what I'm calling out here. So I'm using matplotlib.pyplot to plot these visualizations out. And in this one, I'm using Seaborn, which was SNS. If I went back up and showed you that I'm replacing Seaborn with SNS, this is what it's doing. Seaborn is actually kind of a layer built on top of matplotlib, although it isn't the same library. But it creates more, I would say, fancier, more detailed visuals than matplotlib, but just another visualization option. Here we're doing a box plot, again showing distribution, but this one adds whiskers to it so I can kind of see, what the minimum and maximum values were. So the minimum's always going to be 0. Can't go less than 0 on a trip. Can't go negative on a trip, can't go negative on a fare. That'd be messed up if that happened. But we can see what, the max values are. And then it gives me, median and 25% and 75% quartiles on this. All right. We're getting way too much into that. Love talking about it. Here, we're just doing another box plot that more visually represents any outliers that might be contained within this. And again, we're doing a matplotlib scatter plot. So several different visualization options that I can apply with pandas-based visualization packages. If I want to use Spark, then I can convert it to a Spark data frame and then do a display method. And then I could take this table and create my own charts and visualizations with it. So this is how we utilize Spark to run notebooks. So this is the underlying engine, just showing you how you can use visualization techniques, how we load data in, and why it has to be in a certain type of data format, whether that be a Spark data frame, a Pandas data frame, or a table or view, so that we can utilize these different tools to query it. Great. Let's head back into the studio.
Great job, detectives. You have learned a lot about how to use Spark and Fabric to load, transform, and query data using data frames and SQL. You've also seen how to create and run notebooks in Spark jobs, as well as how to create stunning data visualizations with various Python libraries. Now you're one step closer to applying your skills to solve any analytics mystery that comes your way. Thanks for joining.